Hi everybody. In this video I'm going to do an example problem in which I use Faraday's law to find the current induced in a loop of wire placed in a changing magnetic field. Okay, here's the setup. Imagine I've got my x direction to the right, my y direction up, and my z direction out. I've placed a square loop with each side with this dimension, and the face of the loop is in the plane, in the xy plane. Imagine that this conducting loop has a resistance of 0.100 ohms. All right, so now let's talk about the changing magnetic field. Imagine that in a period of 0.2 seconds, two-tenths of a second time interval, the magnetic field changes from this vector to that vector. Now, let's look a little more closely at this and see what's going on. Going from the initial magnetic field vector to the final magnetic field vector, basically the x component has gone into the y component has gone into the z component, and the z component has gone into the x component. So what physically might be going on? Well, imagine I've got x, y, and z components of the magnetic field. Basically what this amounts to doing with this swap is basically swapping those components of the magnetic field like that. So that could be done, for example, by having some external magnet with a north pole and a south pole. You got some magnetic field with x, y, and z directions, and all you do is rotate the magnet. That's how this could be done. Okay, so now that we've imagined how this could actually happen, let's go and see if we can calculate the problem. A couple more things to take care of. We're assuming that this magnetic field is uniform. If it wasn't, then in order to calculate the magnetic flux, in the initial and final states, we need to do an integral B dot dA over the full area. But we're assuming the magnetic field is uniform, so we can use a simplified formula for magnetic flux. Second thing, I need to choose an area vector for doing this calculation. I could choose out of the board or into the board. I'm going to choose out of the board. And so if I want to represent that abstractly, I could have my area vector equal some magnitude, a positive number, times a z-hat direction. That would be a vector this way. Okay, so now we're ready to go. So we're going to use Faraday's law of induction. Now, if we had knowledge that was instantaneous, we could use the instantaneous version of Faraday's law. But all we can do here is calculate averages. We know an initial magnetic field, a final magnetic field, and some time during which it's gone from initial to final. But we don't know how exactly that's happened. So we need to use this average version of Faraday's law, I like to call it. To have the instantaneous version, these deltas would change to differentials. Okay. So let's go. I can replace the average induced EMF, the average induced voltage, with the current going through this resistor times the resistance of that resistor. Basically what we're imagining is, there's no power supply here. But if we did have a power supply, we'd have voltage gain across the power supply and a voltage drop across the resistance of the loop. Well, there is no power supply, but the Faraday's law voltage that's generated through this Faraday's law process will take the place. It will be mathematically the same as a power supply. So we've got a voltage provided to the circuit, for lack of a better word, by the Faraday's law process, and then dropped across the resistance. All right, so I'd have I average R, but that's the resistance of the loop. All right, I'm just going to write this out. All right. And I'm going to drop the B subscript because we know this is magnetic flux, and I'll just have final flux minus initial flux. Delta is final minus initial, and this minus sign. I can distribute the minus sign out or through, so I'd have minus final flux plus initial flux. So I'm going to do that. Okay, and now what I'm going to do is I'm going to plug in for this magnetic flux expression for the initial and final, noting that the area vector is not changing, but the magnetic field is. So in each case, I'm going to have the same area vector, but I'm going to have a different magnetic field vector. All right, a couple more steps. What I'm going to do is I'm going to divide both sides by r, and I'm also going to factor out this area vector, right? I've got this bi dot a minus bf dot a. So I can factor out, now dot products are not the same as ordinary multiplication, but you can still do factoring with dot products in the same way that you can with ordinary multiplication. So here we go. All right. So now we've got a couple more steps. I didn't actually have to do this. I could grind out this dot product, grind out that dot product, subtract the two numbers, and do the other steps. But this is going to be nice and slick, and it's going to help save me some space on the board. All right, so what I'm going to do is I'm going to actually plug in for this, so just so we can see what's going on. So I'm going to subtract B final from B initial component by component and plug in here. B initial minus B final, I'll have an X component, a Y component, a Z component. So just for the X component, I'd take this minus that. For the Y component, I'd take this minus this. For the Z component, I'd take that minus that. All right, so I'm going to do that here. Okay, so let's just check that. I'm going to make sure I've got this correct. So all of this is all of this right here. So I've got 1 minus 1.75, that's minus 0.75, that's good. I've got 3 minus 1, that gives me 2, that's good. And I've got 1.75 minus 3, that's negative 1.25 units of Tesla in each case, and I need this to be a z hat. All right, and then I've got my denominator. All right, so now I'm going to work this dot product out. This, dotted with this, will be this dot this, plus this dot this, and then this dot that. X hat dot z hat is 0, y hat dot z hat is 0, because any two directions, any two vectors that are perpendicular to each other, their dot product will be 0. But z hat dot z hat is 1. So I can simplify the numerator by basically this dot that disappears, this dot this disappears, and I'll just be left with this dot this. So I'll do that. I'm going to erase this here to create some space. All right, so all that comes out of this dot product right here, I've got minus 1.25 Tesla z hat dot a z hat. Z hat dot z hat is 1, so I'm left with a minus 1.25 Teslas there, the a right there, and then my r delta t in the denominator. All right, so if I plug in for the area would be 0.0500 times 0.0500 meters, so I get meters squared, divide by the resistance of the loop, which is 0.100 ohms, divide by the time interval during which this process takes, which is 0.200 seconds. I get, for my final answer, minus 0.156 amps. All right, and that is the average induced current. We're not quite done yet. I mean, if all we wanted was the value, the amount of it, well, the absolute value of this is 156 milliamps. Great. But which way is it going? Well, we can use the sign conventions from Faraday's law to figure this out if we're careful. Remember, there's a right-hand rule relationship between the area vector choice and the positive direction around of the perimeter path, which would also be the positive direction of the current. All right, so my area vector's out. I stick my thumb in the direction of my area vector. My fingers represent my fingers wrap around in the direction of the positive path around the perimeter, which would be the positive current if we had a positive current. But we had a negative current, so the current ends up going the other way. So what I'm going to do is how I'm going to represent that. I'm going to go this way. And then I'm just going to write I average. I'm going to put it in absolute value. So we know that there's an amount of this. I average equals absolute value equals 0.156 amps. All right, so there's the amount, there's a direction. That's encapsulated here if we're careful with our signs in Faraday's law. Okay, I hope that helps. That's just one more example with Faraday's law. Thanks for watching.